there and welcome. You're about to watch a Lakehead International live webinar. It is a great way to explore what Lakehead University is all about. In this session, you'll hear insights and stories from Lakehead professors, staff, and current students. While watching, if you have any questions, feel free to drop them in the comment section below. For now, let's dive in.
All right. Hello, everyone, and welcome to today's session. Thank you so much for joining us today. My name is Hardika Narankar, and I'm part of the Lakehead International team. I will be a host for today's session, and we are really excited to have you here for an engaging session titled Introduction to Graph Theory, or you can just say like why almost everything is a graph. And with that, now it's my pleasure to introduce today's speaker. Joining us is Dr. Moira MacNeil, Assistant Professor in the Department of Computer Science at Lakehead University. So without further delay, I'll just now hand it over to Professor MacNeil, and she'll be taking today's presentation ahead.
Great, thank you so much. Let me share my screen. Okay, so firstly, I just want to welcome everyone to this session. I will encourage you to interrupt me. There's nothing I love more than a question. So please feel free to use the chat. I'll try to keep an eye on it. And maybe if I miss something, one of our lovely hosts will point that out to me. Yeah, so let's get started. So my name is Dr. Moira. I've been in the Department of Computer Science now for nearly a year. So this is my first year at Lakehead. And today we're going to talk about why almost everything is a graph. So you can think of this as your first lecture in graph theory. And this is a more theoretical aspect of computer science, is something I find very interesting and kind of that underlies a lot of the research and teaching I do. Let's start it. So we're going to start with a very old motivating example that dates back to the 1700s. So there is this well-known graph problem called the 7 Bridges of Königsberg. The town of Königsberg is in what is now modern-day Russia, and it's divided by this river. So it basically creates a bunch of little kind of islands that happen here. Right? And to connect the town, we have all of these bridges. So there are 7 in total. And those bridges allowed people to get from different parts of the town to the other. And so Swiss mathematician Euler, who is commonly thought of as the father of graph theory, asked a very simple question, which is that if you were to go for a walk starting at any point in the town, so any of these kind of hatched areas, if I were to start here, can I go for a walk that takes me over each bridge exactly 1 time? And so I have a little poll because I think I would like to know what you think. Let me see if I can start. There it is. Let's see. What do you think? Can we walk over each bridge exactly once? Seems like it's pretty close in terms of what we're thinking. All right. So seems that yes is winning. We're about 50% yes, 30% no, and 20% not sure, which is always a valid option, right? We're here to learn. Someone in the chat is saying it depends on the distance, which is interesting. So let's take a look. All right, so let's try. This is always the best approach to a problem like this, especially one where we can look at it because it's relatively small. Let's imagine that we start over here. So imagine I start in this area. Well, first we can kind of make some observations. We see that in order to get over here, there are 1, 2, 3 bridges. All right, so bridges 1, 2, and 4 cross into this area. That means if I cross bridge 1, I can leave. If I come back over bridge 2, I can stay in that area and then have to leave again via bridge 4, or some combination of those, right? We could take them in any order. So that means if I start in this area, I cannot end in the area because I have to cross back out. Okay, so what if we consider now starting in this tiny island in the middle? It has 5 of the 7 bridges that connect to it. That means, in a similar way, if I start there, I cannot end there. Right? So I have to leave once, come back in, leave again, come back in, leave again. So if I start here, let's call this area A, then I have to leave, right? So I can't end in area A. So I could end in area B, right? But the issue is then if I consider this last one on the other side, and we'll ignore this one over here for now, if I have the same issue in area C, where I can either start there and not end there, or end there but not start there, right? So the answer to this question is actually no, right? With this configuration, with these numbers of bridges, there's no way to walk over each bridge exactly once. We have to do a repeat. Okay, so I've told you this is a graph problem, but without actually telling you what a graph is. So this is one of our very first examples of a graph problem. Graphs are very general mathematical structures that basically let us represent relationships between pairs of objects. Right? So we have all kinds of uses for graphs. They're especially useful when we're not interested in the physical properties. So someone in the chat said the answer to that question is going to depend on the distance. But what is so great about graphs is that they allow us to abstract away some of the information, right? We didn't care what the distance was between bridges, how long they were, you know, whether they were made of wood or metal, what the terrain looks like, if there are hills around the bridges, all of that stuff doesn't help us answer the question. And so graphs allow us to model that in a way that's very straightforward. And so a graph, formally, is just a set of what we call vertices. So these are the objects. And normally when we draw them, we represent them as circles. Okay, so these are a couple of circles. This is object I, and this is object J. And also a set of edges that connect them. So we use lines to connect our objects. And of course, we can have many, many objects and many, many edges. And that's usually what's most interesting for us in kind of the modern world in terms of using graphs. So let's see what our 7 bridges problem looks like as a graph. Right, so before I kind of labeled the sides of the river, we have A up here, B up here, C, and I'm going to call this one over here D. And these are actually our vertices. Right, so the vertices in this problem are the, say, land, and the edges are the bridges that connect those pieces of land. So if we were to draw this as a graph, we're going to put each one of those pieces of land into a vertex. See, and I'll put D over here. And then we're going to connect them, right? So using each one of the bridges, we can see that there is 1, 2 bridges from A to B. And so I'll draw them like this. 2 parallel lines here because we have 2 options, 2 bridges to cross from A to B. We can also see that there is this bridge over here from A to D, like So we have a bridge from D to C, a bridge from B to D, and then two bridges, number 5 and number 6, from B to C. Okay, so on the left, we have our kind of physical representation, our map of our town of Königsberg with the bridges, but we can also think of it in this way on the right as just a graph. Right? We're not interested in the actual topology or anything like that. We're just wondering which pieces of land are connected by which bridges. And then the problem becomes, can we trace all of the edges here in one single walk without having to repeat any of them? And the answer is no, we always miss one of them. This is a very simple example. As I said, it's one of the first examples of graph theoretical problems. But we have tons more that we can see. So I have some real world examples for you. The first one I like to give always is the idea of a social network. So this is what this picture is on the right-hand side. We can see that each one of these black dots is a vertex and they're connected by edges. And in the case of a social network, you can think of each person being a vertex and a friendship or a relationship being an edge. You know, this also counts for things like, you know, your online social networks as well, right? If you're on Instagram, a follow could be an edge and each account is a node. We can think of, like we saw in our bridges of Königsberg example, right? Our locations, our towns, our vertices, the roads form the edges. We even have lots of examples in more applied biological situations. So something like the nervous system, we can model as a graph where the neurons are vertices and the edges are connections between them. This is a huge area in terms of computational neuroscience, trying to kind of model the brain and figure out how those structures interact with each other. We also, of course, have the internet. That's maybe one of the biggest examples of a graph. So each website is a vertex, and we have an edge from a website to another if they link to each other, so they're connected in that way. One that's a bit more abstract is in the case of scheduling. So graphs are actually really useful in terms of solving scheduling problems. So the example I'm giving here is of course scheduling, where we let each class be a node, and there's an edge between them if that class has the same person if two classes have the same person in both of them. That would mean that they couldn't happen at the same time. So that's kind of an example of a conflict between them. So we'd have to make sure that those two classes are not happening at the same time. And of course, there's so many more. Almost anything you can think of can be modeled as a graph, which is why I titled my talk what I did. But there is one caveat. And so for us, for our purposes, a graph is not the graph of a function like we see here. And it's not like a bar chart or a bar graph or any of those kind of more data modeling pictures. Right, so we have to be careful because this is a word that gets used a lot in a bunch of different areas, and we need to make sure to differentiate between what we're talking about. So a few problems that graphs help solve, just again to kind of help motivate why we study this. So you've seen that we can represent lots of things as graphs, and so they help us solve all kinds of problems across a huge number of application domains. So as I said, scheduling is one of them. That's a huge application area. Everything from scheduling sports games to class and exam timetabling to scheduling airlines. More kind of direct hardware applications like designing wireless networks, where we can think of, you know, each vertex is a router and the connection is an edge. Things in more machine learning applications like image segmentation. In chemistry, we use graphs to try to model chemical compounds and understand their structure. vehicle routing and delivery planning. So a graph can be used to help us decide, where your Amazon delivery driver goes and which stops they make and in which order, and so very many more. All right, so let us get into our very first graph example. Before we do that, we need to make our graphs a little bit more fancy. So far we've only seen graphs that have vertices, right, I and j, and they're connected by an edge, right? And in this case, our edge goes in both directions. I is related to j is related to I. We can also define a directed graph. So in this case, we have our representation as an arrow, right? So this says whatever relationship we have between I and j is ordered, right? I goes to j, but not necessarily is there a relationship from j back to I. You can think about this as, followers on social media, right? So this is maybe saying that I follows the account of j, but j doesn't necessarily follow I back. Of course, we could also define an edge back there. Okay, so this would say both I and j follow each other on Instagram. The other thing we can do is add weights to our edges. And this is really helpful when we are trying to model things like distance, like time. Adding some of these extra attributes to our graph edges can be really useful. And so here's our graph from before, and we could say something like, the distance from I to j is 3. Right? So maybe this is a measure of time, 3 minutes, 3 hours. Maybe it's a measure of distance or some other kind of metric that tells us something about the relationship between I and j. And so the problem we will study today uses both of these concepts at the same time. The idea is that we're going to look at, for example, a graph that is modeling your commute to school, right? So home is up here. You have 4 friends' houses that lie between you and school. So I just gave them all letters A, B, C, D. And this is school, right? And maybe your town is filled with tons of one-way streets, right? So I can go from my house to A, but going back, I can't necessarily take the same image. And so the idea is, right, you want to get to school, but you have the option of visiting any of your friends on your way to school, right? So you could go to A, then visit C, and then head to school. But we're busy, right? Maybe you have an 8:30 class and you don't want to wake up too early. And so you're trying to get to school in the most efficient way possible. And so we're wondering, right, if each one of these numbers, each one of these weights on the edges represents the amount of time it takes you, we wonder how long it will take to get from to any other vertex. Right? And in fact, because we want to get as much sleep as possible, maybe we're interested in knowing how long it takes to get from home to any other vertex with the shortest amount of time. And so that leads to our first formal graph problem, which studies something called the shortest. So we're going to start with one of those graphs. It has weights and directions. And we use the function W to represent the weight. Right? So if we have an edge that we call E from U to V, then the weight of E is I don't know, for example, 7, because it takes 7 to get from A to B. And we'll often talk about paths. And so a path is just any sequence of vertices that we visit in our graph. Right? So we could go from I to J to K, and that'd be our path. And if we have 2 edges here, then the weight of the path would be 3 plus 7, so 10. So what we're interested in then is this idea of the shortest path. The path that takes the minimum weight between any pair of vertices. Right, so if we go back to this previous example, and there's some edge that goes directly from I to K. We'll call that P2. From I to K. And this has weight 4, then P2 is our shortest path here. So oftentimes, we're not just interested in picking 2 vertices and finding the shortest path between them. We sometimes would like to pick a single vertex, for example, the home vertex in that example I showed you, and find the shortest path from that vertex to every other one in the graph. Right, so my example is from home to all other vertices. And that is the problem we will solve. So for us, we're going to assume that all of the edge weights are at least 0, right? So maybe they're somewhere so close you can basically teleport there, and that's all. And we also have to be careful because there might be more than one shortest path, right? So there are options. We also have this nice structure that if we have a subpath of a shortest path, it's also going to be the shortest path. So for this algorithm, right, to be able to solve this problem, we need to keep track of 2 things. The first thing is that for each vertex, we need to keep track of what we call its predecessor, and we use pi to denote that. This is the vertex that's going to be before it in the shortest path. We also keep track of an upper bound on the weight of a shortest path, right? So when we start, we have some estimate. Maybe it's infinity because we don't know how far apart 2 vertices are. And with every step of the algorithm, we're going to keep updating that until we get to the actual shortest path. So our first step is to initialize all of this for every vertex. Right? So we'll start by setting our source vertex, the S. Its distance to itself is 0. And then for every other vertex, our distance estimate is infinity, and we have no predecessor. So we don't know what the step before it in the shortest path. The algorithm that we use uses a sub-procedure to test if we can improve the shortest path to V via U. Right, and if it's the case, it's going to update the estimate and the predecessor. We call this step relaxation. Right, and so we'll call a function we call relax. So we give it U and V and the weight function W. So it basically tests. Right, here's our edge U to V. There's some other path that gets us from S to V with distance 7. This is D of V. And so what we do, right, we know there's some path that gets from S to U with distance 3. My squiggly lines mean there might be some other vertices in between there. And so if we get to U in 3, well, it's actually faster, right, to go to U in 3 and then take this edge to V and get, right, to V in 6 instead of 7. Right, so that's all this procedure does. It checks, okay, is the distance to V larger than the distance to U plus the edge from U to V? And if so, it will update it appropriately. Right, so now U becomes the predecessor of V, and we have an updated weight. So the main idea of our algorithm is we're going to maintain a set of the vertices where we've calculated the shortest already. And at each step, we pick the vertex with the smallest estimate, add it to the set, and then relax all the edges, leaving it. Right, so basically check if we fix U, can we update any of the V? We'll use what's called a min priority queue to keep track of these minimum elements. This is a data structure that basically lets us efficiently pick the smallest element. So that's the one with the smallest distance estimate. And so just to caution you that this only works with non-negative edge weights. So we start by initializing with all of our edge weights and predecessors and setting our set equal to 0. And then adding all of the vertices to that special queue that will help us pick those elements. And then while we haven't checked every vertex, we pick the minimum element out of queue, we add it to the set, and then for every edge that is adjacent to U, right, so every neighbor of U, we relax. All right, let's see an example. So this is our original example. And here I have put the distance estimates inside the vertices. So this is our D of S, D of B, right, is inside. So we start with S being 0, everything else being infinity. We've added all of our items to the queue. And here I'm just using a list. So the leftmost one is the smallest one, and that's the one we're going to remove. So in the first step, we're going to pull S out because obviously 0 is the smallest element. And we are going to relax the edges to its neighbors, which are B and A, right? So we can update this estimate from infinity to 2 and infinity to 3, and S will become the predecessor. All right, so the highlighted edges are showing us the shortest path, right? That's the idea of the predecessor. And now B is our smallest element, so we'll pull it out and then relax all of the edges here. So there's only 2. Obviously, when we add 2 to 8, we get 10. And so the shortest path to A is not going to update, but the shortest path to C is going to update it because 2 plus 3 is less than infinity. So we get 5 here. A is our next smallest shortest path estimate. Again, when we relax its one out edge, we can see that 3 plus 9 is more than 5, and so nothing will change. We add it to S. Again, now C has our smallest estimate, and so we'll relax the outgoing edges here. As you can see, that we get a shortest path of 5 plus 6 to D. But now E is our next smallest element, and there is an alternate path via E, which we can take, which will have distance 9, and so this will update instead. Okay, and so of course we'll pull 9 out, and that will be our final option here because 9 plus 5 and 9 plus 4 is greater than our 2 options. And so this is our final shortest path, and we can see that if we choose one of these highlighted edges, right, it gives us the shortest path to any of the other vertices if we start. So just to round us out, usually when we're talking about algorithms, we have some kind of important questions that we ask. And of course, that is not something we have time to do today, but I'll just leave you with those so you can start to think about these a bit more like a computer science. Right, so Dijkstra's algorithm. We want to know things like, how long does Dijkstra's algorithm take? Right? Of course, this is going to depend on the number of vertices and the number of edges, right? So the length it takes depends on the graph size and on the structure. So oftentimes we talk about, in the worst case, how long does the algorithm take if we're given a very general graph? Yes, exactly. Someone in the chat has already said that as well. A very important question is whether or not we're guaranteed to get the shortest path every time, right? So if we give Dijkstra's algorithm a graph that has non-negative edge weights, do we make sure to get the shortest path every time? The answer is yes, but we should always be thinking about why, because the idea here, right, I give you a very small example with 6 nodes, but think about solving that on, a graph that represents a social network with millions of people in it. Is it possible to solve it? And the answer is yes. Of course, we've made a pretty big assumption, which is that our edge weights can never be negative. And so maybe if our edge weights are representing some kind of score between 2 items, they could be negative. Can we find a solution if the edges have negative weights? The answer is yes, but we have to use another algorithm. Okay, so this one does not work for us. And my final question is, does the graph have any special properties that will let us use a faster algorithm? And I'm seeing in the chat here that someone is talking about Google Maps, which is a great example of a shortest path algorithm, right? You're trying to get directions to go somewhere. It's going to give you, hopefully, one that's going to take you in the shortest path, or approximately the shortest path. And so someone very intelligently pointed out, they use the A-star algorithm, right? So sometimes we know more about our graphs, and so there are special properties that let us use something that's going to speed it up and make it faster. And with that, I think I might be a little bit over time, but I will leave you, and I'm happy to take any questions. I should also mention that I'm the co-op officer for computer science, or faculty representative, so I'm happy to take questions about that as well. I don't know that I'll have all the answers, but I'm happy to help. So thank you so much for your attention.
All right. So now we'll move on to our Q&A session. So feel free to ask any questions you may have for our professor, and they will be able to answer it for us.
I'm just checking I didn't miss any in the chat as I was going.
Yeah.
I don't think so.
We'll just wait a few more minutes
Yeah,
for
of
any
course.
questions to pop up, and then if there are no more questions, then we'll just wrap up our today's session.
This is a good question from Paula, who asks, what makes a successful computer science student, in my opinion? That's a tough question. I think that a successful computer science student is maybe the same as a successful student in any subject, which is someone who is willing to ask questions when they don't understand, and willing to think deeply about problems. And I think computer science, especially when we start talking about programming, requires a lot of grit, right? Oftentimes we end up with problems that are challenging to solve, and that we have bugs in our code, or things don't go quite right. So I think that kind of that grit and that ability to keep trying on a problem that's giving you challenges, it makes a good computer science student. So someone asked, I've heard that in Dijkstra, if you are not using infinity but an estimated distance, you can improve the performance. Yeah, so this is, the algorithm I showed you today is kind of the very bare bones, most basic kind of introduction. There are lots of ways that we can improve these algorithms. So definitely improve distance estimates is one of them. The way that we implement it as well, like I just showed you kind of very high level pseudocode. So the way in which we implement it, the data structures we use, all of that can help speed stuff up. All the way up to very complicated ideas like starting to use randomized techniques that give us kind of a performance bound instead of actual performance. It's a very good question. I cannot answer any questions about admissions, but I will say that if you're interested in exploring some of the topics that you'll see in the courses, the Department of Computer Science does have on their website many of our course outlines posted. So usually the ones from the last year or two. So you can take a look at the syllabi, the course outlines, and kind of see what you could expect in each of your courses, which is really useful in terms of trying to decide on a program and also if you're interested. This one is about co-op. Just wondering how the co-op market is for Lakehead students. I will say the job market is challenging in general, but and that is not just for co-op students, that's for everyone. Our co-op students, when they do get jobs, they tend to do multiple terms. Like it's very common that we'll see students who are asked back for another term with the same company. And we have a few students this year who are actually getting job offers for after graduation. So I think the co-op program is, it's one of the best things you can do. And it's really useful, especially going into a challenging job market after graduation.
So there is a question about application decisions. So the timeline for the application decisions may vary. So I would just, since it's just been 1 month, 2 weeks now, I would suggest you can, keep a check on your student profile and also on your email. But if you still have no update, you can reach out to the admissions team and they'll be able to help you with the status of your application. Just make sure to put the student ID and the application number.
There's a couple more that came in. This one is related to our very STEM hub. And so which is new and opening this fall, which is very exciting for us. The curriculum is the same. You will have different professors than if you were here in Thunder Bay, but my colleagues who have been in Aurelia and now are moving to Barrie are excellent and will absolutely be teaching the same curriculum. Some of our courses are offered online, so you might be able to interact with students from the other campus, but it's absolutely, you're getting the same degree at the end of it. So
There is a question just asking about how the first year in Lakehead would look like.
So that's kind of an open-ended question.
Oh, okay.
I guess in computer science, we have you'll be taking mostly introductory kind of courses, and then more discrete math course, which will focus maybe slightly more on the problem, something like I showed you today. Introductory level programming courses. I will say that kind of the caveat here is, you don't need to know how to program or be an expert programmer when you come into a computer science degree at the undergrad level, which is very nice. We kind of assume that you don't know anything. Like, for example, when I started my degree, I had never programmed before. And so don't worry if that is not in your skill set yet. That's what we're here to teach you.
There is another question. So what are the limitations of the algorithm that you just showed, and also programming languages do we learn through the course of BSc Com?
Okay. Limitations for this algorithm are obviously the fact that we can only do it on positive or non-negative weight edges. Usually when we start to talk about these kind of shortest path algorithms, the limitations happen when our graphs get really large. And so we need ways to be able to process things without doing many iterations. And so those limitations come with size, but we have ways to get around them and kind of improve upon them. So again, beyond the scope of just this lecture, but that's definitely something you'll be able to explore during your degree. In terms of programming languages, lots. The answer is lots. So you'll see C and C++, Python probably as you get kind of higher up into things. I'm not sure if we're teaching Java right now. My courses are mostly related to programming. SQL, so like database query languages, you'll get a pretty well-rounded exposure to lots of programming languages as well, which is very nice. And someone says, basically, computer science is like thinking out of the box, and that is true. I think that computer science and a computer science degree teaches you the real life skills of being able to program and actually use computers and develop software, but it also helps you a lot with that abstract thinking outside the box, being able to solve problems, which are helpful across all kinds of areas of your life, not just developing software or making apps.
All right, thank you so much. So there is a question again based on admission related. I will answer that. So Chris, once all the required documents have been submitted, usually graduate admissions at Lakehead just gonna typically take about 6 to 8 weeks, sometimes even longer, depending on the workload that they may have. I know the admissions team as of now is working very hard to get all of those decisions out soon as possible. So yeah, it also depends on the program that you have applied to, the supervisor and the departmental review, and also the volume of applications. So I would just say that if you have applied and if you're waiting for some decisions and it's been a long time, you can reach out to this admissions team and they'll be able to help you. There's another question. What about statistical fields? Can we use graph too?
Absolutely. Something I'm not as familiar with, but this is definitely an underlying structure we can use to represent a lot of problems, right? So we can think about those edges having, instead of a fixed weight, maybe it follows some probability distribution. Maybe they, the objects appear with some probability. So there's all kinds of extensions beyond the kind of fixed graph structure. This is maybe appearing more in things like networks optimization, right? Where we might have two routers and the connection between them might not be fixed. It might be, different speeds or something like that. So definitely lots of extensions into more kind of statistical randomized settings as well.
Right. So let's just wrap up today's session. So thank you everyone for joining us today, and a very big thank you once again to Dr. Moira for such an insightful and engaging lecture. So today's session actually gave us like a fascinating introduction to graph theory and just showed us how mathematical structures can help us understand like real world systems all around us. Yeah, so thank you to everyone else who joined from different parts of the world. We truly appreciate your participation. And if you'd like to stay connected with us beyond today, you can reach out to us on social media. We're there on Instagram, Facebook, and YouTube under Lakehead International. And yeah, thank you so much for joining our session today. Have a wonderful day, evening, where you're joining from. Thanks again. Dr. Moira, do you have any final words before we wrap up today's session?
No, thank you so much for having me, and I hope to see everyone on campus in the fall. So take care.
Thank you. Bye-bye.
Bye.
Thanks for watching. If you have any questions, feel free to drop them in the comment section below. You can connect with us on social media. You can find us at Lakehead International on Facebook, Instagram, and YouTube. We hope to see you in our next live webinar. Bye for now.